Previous year question and answer solution of Stream Electronics and Communication Engineering, Semester 3 subject, Data Structure and Algorithms, LAQS. Question 1. Create an AVL tree by inserting the following numbers in the order in which they are given: 17, 25, 19, 23, 75, 6. Explain it stepwise with suitable diagram. What is threaded binary tree? What are its advantages? Answer: A. AVL tree insertion. AVL definition. For reference, an AVL tree is a height-balanced binary search tree in which, for every node, BF equals HEnder minus HRR less 1, where HL, HR are heights of left and right subtrees. Stepwise insertion, BST plus rotations plus diagram notes. 1. Insert 17. Tree. Only one node. 17 is root. Heights. H of 17 equals 1. BF of 17 equals 0. Balanced. 2. Insert 25. BST insertion. 25 greater than 17 goes to right of 17. Tree. 17, root, right child, 25. Heights. H of 25 equals 1. For 17, HL equals 0, HR equals 1. BF of 17 equals -1. Still balanced. 3. Insert 19. BST. 19 greater than 17, arrow right to 25. 19 less than 25, arrow left child of 25. Temporary tree, before rotation. 17 right arrow, 25 left arrow, 19. Heights. BF of 25 equals +1. For 17, HL equals 0, HR equals 2, arrow BF of 17 equals -2, arrow unbalanced at 17. Case type. New node, 19, is in left subtree of right child of 17. RL rotation. Right, left. Rotations. Right rotate at node 25. Subtree becomes 19 as parent, 25 as its right child. Left rotate at node 17 to 19 becomes new root. Balanced tree after rotations. 19 root left to 17 right to 25. 4. Insert 23. BST. 23 greater than 19 go right to 25. 23 less than 25, left child of 25. Tree. 19 left, 17 right, 25 left, 23. Heights. BF 25 equals +1. BF 19 equals -1. Balanced. No rotation. 5. Insert 75. BST. 75 greater than 19, right to 25. 75 greater than 25, right child of 25. Tree. 19 left, 17 right. 25 left. 23 right, 75. Heights. BF 25 equals 0. BF 19 equals -1. Balanced. 6. Insert 6 BST. 6 less than 19, left to 17. 6 less than 17, left child of 17. Final AVL tree. 19, root, left subtree. 17 left, 6 right, empty right subtree. 25 left, 23 right, 75. Heights. H of 6 equals 1. H of 17 equals 2, with BF of 17 equals +1. H of 23 equals H of 75 equals 1. H of 25 equals 2, with BF of 25 equals 0. Root 19. HL equals 2, HR equals 2, BF19 equals 0. No further rotations needed. Tree is AVL. Diagram hint for answer sheet. Draw each step as above. Clearly show the RL rotation after inserting 19 and final AVL tree with 19 as root, 17-6 on left and 25-open parenthesis 23,75 close parenthesis on right. B. Threaded binary tree. Definition. Use Horowitz and Sahni threaded tree idea. In a normal binary tree, many left-right child pointers are null for missing children. A threaded binary tree is a binary tree in which null child links are replaced by special pointers called threads. A left thread at node P points to the in-order predecessor of P. A right thread points to the in-order successor of P. Two extra 1-bit fields, L bit and R bit, are stored with each node. L bit equals 1 if L child is a normal pointer, 0 if it is a thread. R bit equals 1 if R child is a normal pointer, 0 if it is a thread. Trees may be single-threaded, only one side threaded, or double-threaded, both left and right threads. Often a head node is added so that external threads, first predecessor or last successor, also point to a valid node, not null. C. Advantages of threaded binary tree. From threaded tree discussion and in-order traversal algorithms. Efficient use of space. All n+1 null links in a binary tree are reused as threads, so pointer space is utilized rather than wasted. Traversal without stack or recursion. In-order successor of a node can be found directly using threads, procedure insuc. So in-order traversal needs no stack or recursion, still O of n time. Simpler traversal algorithms. In-order, pre-order and post-order traversals become simpler because successor-predecessor information is embedded in the threads. Easy bidirectional navigation. With both left and right threads, moving to next and previous nodes in order becomes straightforward. Faster in practice. Fewer pointer chasing steps and no stack overhead generally result in better constant factors for traversal on large trees. Question 2. Define queue and its applications. Write an algorithm for insertion and deletion from queue. Answer. A. Define queue using Horowitz and Sahni concepts. Definition. A queue is a linear data structure in which insertion takes place at one end, rear, and deletion takes place at the other end, front. It follows the FIFO, first in, first out principle. Properties. 1. Queue is an ordered list where the first element inserted is the first to be removed. 2 operations. NQ, insert, at rear dequeue, delete, from front. 3. When front greater than rear, the queue becomes empty. 4. When rear equals max minus 1, the queue becomes full for linear queue. 5. Represented using arrays or linked lists. B. Applications of queue from text concepts plus standard DS applications. 1. Job scheduling, CPU task scheduling, printer spooling. 2. Simulation, traffic systems, customer service counters, call centers. 3. Data flow management, buffers in communication systems, I/O devices. 4. Level order traversal, breadth first search, BFS, uses queue. 5. Interrupt handling, devices requesting CPU attention in arrival order. 6. Network routers, packet queuing before transmission. 7. Real-world queues, ticket counters, bank service lines. C. Algorithm for queue insertion, NQ. Linear queue using array from Horowitz and Sahni style. Algorithm. NQ, Q, item. 1. If rear equals max minus 1, print overflow and exit. 2. If front equals minus 1 and rear equals minus 1, set front equals 0, rear equals 0. 3. Else, rear equals rear plus 1. 4. Set Q rear equals item. 5. Exit. Algorithm for Q deletion. DEQ. Algorithm. DEQ, Q, item. 1. If front equals minus 1, print underflow and exit. 2. Set item equals Q, open bracket, front, close bracket. 3. If front equals rear, set front equals -1 and rear equals -1. Q becomes empty. 4. Else, front equals front plus 1. 5. Return item and exit. Question 3. A. Define circular linked list and double linked list. B. Write an algorithm to delete an element from double linked list. Case 1. First node deletion. Case 2. Last node deletion. Case 3. Intermediate node deletion. Answer. A. Define circular linked list. From Linked List Chapter Concepts, Horowitz and Sahni style. A circular linked list is a linked list in which the last node does not contain null, but instead links back to the first node, forming a closed loop. Traversal can continue from any node and eventually returns to the same node. Insertion and deletion at the beginning/end are efficient because there is no null endpoint. Used in round-robin scheduling, buffer management. Both singly and doubly linked circular versions exist. Define doubly linked list. A doubly linked list, DLL, is a linked list in which every node contains 3 fields. 1. Left prev pointer. 2. Info data. 3. Right next pointer. The left pointer links to the previous node and right pointer links to the next node. Traversal is possible in both forward and backward directions. Easier deletion/insertion due to direct access to predecessor and successor. B. Algorithm. Deletion from doubly linked list first node. Horowitz-Sahni standard DLL operations. Algorithm. Delete first L. 1. If L equals null, print underflow and exit. 2. Set temp equals L. 3. Set L equals L arrow right. 4. If L not equals null arrow, set L arrow left equals null. 5. Free temp. 6. Exit. C. Algorithm. Deletion from doubly linked list last node. Algorithm. Delete dist L. 1. If L equals null, print underflow and exit. 2. Set PTR equals L. 3. Traverse while PTR right does not equal null, PTR equals PTR right. 4. Now PTR is last node. 5. Set PTR arrow left arrow right equals null. 6. Free PTR. 7. Exit. D. Algorithm. Deletion from doubly linked list intermediate node. For deleting a node with value item. Algorithm. Delete mid L. Item 1. If L equals null, print underflow and exit. 2. Set PTR equals L. 3. Traverse until PTR equals info equals item. If end reached, print not found and exit. 4. Set PTR arrow left arrow right equals PTR arrow right. 5. If PTR arrow right not equal to null arrow set PTR arrow right arrow left equals PTR arrow left. 6. Free PTR. 7. Exit.
Question 4.
A. Write a quicksort algorithm to sort a list. Explain with an example. B. Prove that the best case time complexity for quicksort is O n log n for input size of n. Answer. A. Quicksort algorithm to sort a list and example 1. Idea: Horowitz and Sani. Quicksort is a divide and conquer sorting algorithm. Choose a pivot element, control key, partition the list so that all elements less than or equal to pivot are on its left, all elements greater than or equal to pivot are on its right. Recursively apply quicksort on left and right sublists. 2. Algorithm: Array A low to high, quicksort. A low to high 1. If low greater than or equal to high, return. 2. Set pivot equals A open bracket low close bracket. 3. Set I equals low plus 1, J equals high. 4. Repeat partition loop. While I less than or equal to J and A open bracket I close bracket less than or equal to pivot, I equals I plus 1. While A of J is greater than pivot, J equals J minus 1. If I is less than J, swap A of I and A of J. 5. After loop ends, swap A of low and A of J, pivot goes to correct position J. 6. Call quicksort A low J minus 1. 7. Call quicksort A J plus 1 high. This matches qsort structure from text. Pivot at beginning, 2 indices moving inward, then recursive calls. 3. Example from text style. Sort A equals open parenthesis 26, 5, 37, 1, 61, 11, 59, 15, 48, 19, close parenthesis 1. First call. Quicksort. Open parenthesis A, 1, 10, close parenthesis. Pivot equals 26. I equals 2, J equals 11. Move I right till A, open bracket I, close bracket, greater than 26. Stops at 37. Move J left till A, J, less than 26. Stops at 19. Swap 37 and 19. A equals 26, 5, 19, 1, 61, 11, 59, 15, 48, 37. Continue partitioning similarly until I greater than or equal to J. Finally swap pivot 26 with AJ. Say position 6, pivot fixed. List becomes left subfile, less than or equal to 26, right subfile, greater than or equal to 26. 2. Recursive calls on subfiles, conceptual. Sort left subfile, e.g. 26, 11, 5, 19, 1, 15, by same process. Sort right subfile, e.g. 59, 61, 48, 37, similarly. 3. After all recursive calls finish, final sorted list 1, 5, 11, 15, 19, 26, 37, 48, 59, 61. Diagram hint. In exam script, draw a table row for each call of quicksort, showing subfiles in brackets and how pivot splits the list. B. Best case time complexity of quicksort is O of n log n, using Horowitz and Sani analysis. 1. Best case assumption. At each partition step, pivot splits the list into two equal halves, sizes approximately n over 2 and n over 2. Time to partition a list of size n is O of n, one pass with two indices. 2. Recurrence relation. Let T of n equals time to quicksort n elements in best case. Then, T of n equals C times n plus 2 times T of n by 2, where Cn equals time for partition, and there are two recursive calls of size n/2. 3. Solving the recurrence. Expansion method. Expand. T of n equals Cn plus 2 T of n by 2 equals Cn plus 2 times the quantity Cn by 2 plus 2 T of n by 4 equals Cn plus Cn plus 4 T of n by 4 equals 2 Cn plus 4 T of n by 4 equals 2 Cn plus 4 times the quantity Cn by 4 plus 2 T of n by 8 equals 3 Cn plus 8 T of n by 8, and so on. Eventually, it becomes k Cn plus 2 to the power k multiplied by T of n divided by 2 to the power k. Stop when subproblem size is n divided by 2 to the power k equals 1, which implies 2 to the power k equals n, which implies k equals log base 2 of n. So, T of n equals Cn log base 2 of n plus nt of 1. Since T of 1 is constant, T of 1 equals O of n log n 4. Conclusion. In best case, quicksort divides the file into two equal halves at each level. Number of levels in recursion tree approximately log base 2 of n, and each level costs O of n. Hence, best case time complexity is T of n equals O of n log n. Question 5. Write short notes on any three from the following. A. AVL tree. B. DQ and priority queue. C. Collision resolution techniques in hashing. D. BFS. Answer. A. AVL tree, from Horowitz and Sani AVL section. An AVL tree is a height-balanced binary search tree where, for every node, absolute BF equals the absolute value of H sub L minus H sub R, and it is less than or equal to 1, ensuring logarithmic height. Insertion and deletion may violate balance. Rotations are used to restore balance. Types of rotations: LL, RR, LR, RL rotations. Guarantees O log n time for search, insert, and delete. Maintains near-perfect balance automatically, making it suitable for dynamic dictionaries and indexing. B. DQ and priority queue, from linear lists and queue structures. DQ, double-ended queue. A DQ allows insertion and deletion from both ends, front and rear. Types: input-restricted and output-restricted DQs. Useful in implementing algorithms like sliding window, job scheduling, and palindrome checking. Priority queue. A queue where each element has a priority and deletion happens based on highest or lowest priority, not arrival order. Implemented using heaps, balanced trees, or arrays. Applications: CPU scheduling, Dijkstra's algorithm, event-driven simulation. 3. Collision resolution techniques in hashing, from hashing chapter in Horowitz and Sani. Collision: when two keys hash to the same address. Common resolution techniques. 1. Open addressing. Probe next locations until an empty slot is found. Methods: linear probing. H of k, I equals h of k plus I, all taken modulo m. Quadratic probing. H of k, I equals h of k plus c1i squared plus c2i squared. Double hashing. Second hash function decides step size. 2. Chaining. Each hash table slot stores a linked list of keys mapped to that slot. Efficient when load factor is high. 3. Rehashing. Expand table size and reinsert all keys when load factor becomes too large. Ensures efficient search insert operations even with collisions. 4. BFS, breadth first search. BFS is a graph traversal algorithm that explores vertices level-wise starting from a source node. Uses a queue to store next vertices to visit. Steps: visit a node. Enqueue all unvisited adjacent nodes. Repeat. Time complexity. O of V plus E for adjacency list representation. Applications: shortest path in unweighted graphs, cycle detection, bipartite checking.